All right, everyone. It's lovely to hear the hum of voices and chatter as we get to know each other and talk through a variety of things over these last couple days. We're on to our final session on environmental impact and societal challenges of desalination and water reuse, and I'm honored to co-lead this with you, Avner. And so we'll start by just telling you about our 4 speakers, and then we'll just get the show on the road. So first we have Ido Barzev. Ido is a faculty member at Ben Gurion University of the Negev. Ido earned his degrees at Bar Ilan University in the Faculty of Sciences, spent time at Yale University as a postdoc, and then returned to the faculty at the Zuckerberg Institute of Water Research in the Stable Care campus. He's an applied and environmental microbiologist, and his research focuses extensively on microbes in various aquatic systems. And he brings to the issue of desalination expertise for the nexus between water treatment and understanding various microbial processes in marine and freshwater environments. For example, Ido is leading I think this is very interesting and worth mentioning, he's leading an international group of scientists investigating various effects of large-scale desalination facilities on the Gulf of Aqaba's coastal ecosystem, including coral reefs, seagrass meadows, and subsurface bacteria. And his students are studying different ways to minimize the nexus between these industries and the aquatic environment. He's also heading a global project on focusing on the contribution of microbes to aquatic nitrogen cycles via denitrification. Oh, no, sorry. Yes, fixation. You can tell it's been a while since I've studied the nitrogen cycle. And he's been developing a sampling kit for fresh water that has been sampling in 42 countries around the globe and analyzing them in his lab with biochemical and molecular methods that give a signature of ecological health in different freshwater sources around the world. So it's really exciting work and far-reaching. Do you want to introduce David?
Of course. It's a personal pleasure to introduce Professor David Sedlak from University of California in Berkeley. David is a Plateau Malozemov, distinguished professor, Department of Civil Engineering, Civil Environmental Engineering, and the director of Berkeley Water Center, University of California at Berkeley. Dr. Sedlak is a member of the U.S. National Academy of Engineering, chair of its Water Science Technology Board, and recipient of numerous awards. He is also the author of Water for All, Global Solutions for a Changing Climate, Yale University Press, 2023. He has also authored several books on water, and Dr. Sedlak serves as the master cartographer of the National Alliance for Water Innovation, NAW, a multi-year research effort of the U.S. Department of Energy, where he directs efforts to create research roadmaps and advancing desalination and advanced water treatment in the municipal, industrial, and agricultural sectors in the United States. I know David personally. He visited Israel. He made a lot of impression of a thinking person who can teach us a lot of things and with a wide mind, and I appreciate. Let me thank you, David, again on having me visiting your department.
All right, after the master cartographer, which I think, by the way, is the coolest title ever, we have the pleasure of hearing from Asnat Gilor. Asnat is also at Ben Gurion University of the Negev, a professor in the Zuckerberg Institute of Water Research. And as not, research focuses on microbial aspects of soil dynamics in arid environments. She is interested in and has been studying the role of perturbations like rain, irrigation, pollution, and mining on soil microbial community composition, structure, and function. Her group has recently been focusing on the effects of various contaminants carried out by municipal treated wastewater to trophic interactions in irrigated soil microbial communities, and I'm looking very much from hearing from you on your perspective.
Well, Professor Amy Childress, University of South California, she's like my granddaughter. I mean, Manny Elimere was my student, and she's his student, and it's so great to be inside a family like this here. Amy Childress is a professor of civil environmental engineering and director of the environmental engineering program at the University of Southern California. Her research team seeks holistic and realistic solutions to the problem of finite water and energy resources. Her team carries out projects on innovative solutions to contaminant and energy challenges, including pressure-driven membrane processes as industry standards, innovative membrane materials and processes, systems of desalination, wastewater reclamation, and colloidal and interfacial aspects of physicochemical processes. Dr. Childress serves as US EPA's Science Advisory Board, as an editor of Desalination, and on expert advisory panels for regional and international desalination and wastewater reclamation projects. Very proud of you.
All right.
Yeah.
And since you're saying proud, I'm just going to also add to the unscripted, she'll hate me, but also next month, Amy is being acknowledged as the 2024 Clark Prize winner, which is the premier American Water Research Prize. So congratulations, Amy. So Ido, would you like to kick us off? Thank you.
So I would like to start by thanking the organizing committee for inviting me today to discuss with you this nexus of seawater desalination and the aquatic environment. I would say that facing water scarcity, Israel has launched a construction of 5 large-scale desalination facilities about 20 years ago that is producing today roughly 650 million cubic meters of fresh water per year. That correspond roughly to 70% of what all Israelis are drinking. Now, we are in the midst of constructing another 2 large-scale desalination facilities, one in the middle of the country and one in the north, that in the short distance will minimize our dependency in natural fresh water. Similarly, other countries like Israel have walked the path of this desalination process. However, what is unique and needs to remember that Israel constructed these large-scale facilities over a fairly narrow strip of coastal environment. Now, the scheme of most of the desalination facilities in Israel is similar. You draw water directly from the coast. It is being pre-treated and then desalinated, transported to our water carrier, and disseminated to the public after post-treatment. However, one should remember that together with desalinating the water, also hypersaline brine waste is discharged back into the coastal environment. As such, this is the nexus that I would be discussing today. In a more poetic way, I would say I see this nexus as the strange case of Dr. Jekyll and Mr. Hyde. Desalination today is one of the most important things for humanity especially during this era of climate change. However, desalination has a dark side that one should remember, and that's the nexus with the aquatic environment. Looking at the ocean, this is how I see it. I see planktonic organisms free-floating in the water column. There could be fish larvae, zooplankton, phytoplankton, bacteria, and others. You can also find large macroalgae like kelp, seagrass meadows, and coral reefs. You would also see a lot of organisms that are roaming the seabed, such as sea snails, sea stars, crustaceans, and many, many others. Under the sediment, you can find also a lot of nematodes and worms, protists, as well as benthic bacteria. All are doing a lot of remineralization and decomposition of organic matter. That's why they are at the basis of the food chain. The first nexus with the desalination industry is the suction of large and small organisms into the desalination facility. The paradigm is whatever goes in never comes out. However, I will focus in this talk on the impact of brine, this hypersaline solution that is a byproduct of the process. Now, it can be discharged in basically two ways, either directly on the coast, also termed as surface discharge, or through pipes to offshore diffuser systems. Regardless to that, one should ask, why should brine matter? Why should it impact? Well, the first thing, obviously, is the hypersaline solution that can cause osmotic stress. When I talk to students about that, you can just imagine taking a grape, putting it in a salty solution, it will become a raisin. The second thing is chemical additives, such as antiscalants, typically used polyphosphonate-based ones. This can cause eutrophication, especially if they are discharged into oligotrophic environments, such as the Mediterranean Sea and the Gulf of Aqaba. Coagulation, or coagulants, such as ferric chloride, can induce sedimentation and therefore change the seabed. I will not talk today on changes in water temperature or traces of metals that are being discharged, such as copper, which is usually indicative of multi-stage flashing. If you would look on a discharge of this brine, it's not trickling out. This is a river of brine that is being discharged 24/7 forever. This discharge, again, goes directly into the coast. When you talk to operators and ask, okay, what's your solution? Solution is dilution. What is happening is that they will take positively buoyant, hot power plant cooling water and mix it up together with negatively buoyant brine. Hopefully, it would be naturally buoyant at roughly 10% salinity above ambient. That should expedite mixing. When we did a huge 3-year survey and monitoring the outfall of the large-scale desalination we have in Israel, we saw that the footprint of this plume, rather if it's on the surface of the water or creeping over the bottom, it's roughly 1 to 3 kilometers square. Sorry, I don't have it as acres or feet. But if you look into the diffuser systems, it's way smaller, up to 1 kilometer. One thing that you should notice is that it should have been naturally buoyant. But when you actually measure it, it's creeping over the seabed. So the organisms that will be impacted are mostly sessile or under the sediment. When we looked into it, we were sure we'll find horrific things. But actually, what we found is for benthic organisms, the numbers were higher next to the outfall, which is different than what we thought. We thought they would be all dead. Also, their activity went super high. Well, not super high, but significantly more than the outfall point. After about 1 year of research, we found out their predators were dying. There were no predators. Mostly foraminifera and nematodes were out of this entire outfall zone because they could not cope with the hypersaline solution around them. Therefore, bacteria were growing. Molecular identification showed that most of them were halophilic, basically salt-loving bacteria. Overall, the important thing that you can remember out of it is that the food web changed. Now you can ask, is change good or change is bad? Let's talk about that over the discussion, but there was change. Next, we wanted to understand what the antiscalants type will impact the desalination area and the organisms. Polyphosphonate baits, which is commonly used, result in a release of phosphate into the environment. We saw that in a recent paper in ESNT. And polycarboxylated base antiscalant result in a carbon enrichment of the discharge area. Looking into phytoplankton, those organisms that do photosynthesis and are responsible for primary production, what we saw, regardless to the concentration of the antiscalant that was based on polyphosphonates, phytoplankton flourished, up to 200% more than the control. Differently, polycarboxylated-based antiscalant resulted in a linear regression of their growth, probably due to competition of other nutrients such as nitrogen and phosphorus. Well, bacteria obviously also need that phosphate, so they grew, because that's a limiting factor in an oligotrophic environment such as the Mediterranean and the Gulf. It was not surprising that they also enjoyed the carbon that was released from those polycarboxylated antiscalants to a point that a different limiting factor occurred, mostly phosphorus. Nonetheless, when you conclude that part, you can see that addition of antiscalants reduce phytoplankton and increase the biomass slightly by bacterioplankton. Differently, phosphonates increase both, and one should ask himself, even after lunch, when everybody are pretty tired, who cares? So we think that operators should care, because in this discharge zone, it's very close also to the intake. So what will happen to feed water quality once you draw it back into the desalination facility? Are you in a kind of a negative feedback loop? My last example for now on those would be on coral reefs and desalination. And this is quite interesting. Coral reefs are ecologically and economically important, I would say super important, to vast regions across the globe. Their coral distribution is rather constrained in a narrow geographical belt. What was interesting is that if you put this belt and compare it to the water-scarce areas across the globe, there's a lot of similarities. Again, unfortunately, I don't have time to talk about that, but please ask me when we discuss. Nonetheless, it highlights the nexus of this coral reefs and desalination. Now, just a short reminder, because a lot of you are engineers. Corals are animals that live in a very, very tight symbiosis with heterotrophic bacteria and algae. They cannot do without them. Under control conditions of the Gulf of Aqaba, we saw that the polyps, those tentacles, basically their mouth, was exposed out, and they were filtering food, feeling nice and dandy. However, once all brine and chemicals were added, something happened. Heterotrophic bacteria left the tissue, and the algae left the tissue. This is causing bleaching, basically the death of the coral. Again, we wanted to understand what different types of antiscalants will cause to these corals. So we use a model coral called Montipoa, and on the bottom, you can see an optical coherence tomography images, 3D images of the coral itself. You can see the polyps there. Again, when we look under bright field microscopy, we can find this goldenish color coming from the algae, showing that the coral is viable. In white, what you see up here is the tissue in a cross-section. If it's white, it means that the tissue is thick and viable. You see the polyp out. However, once polymer-based antiscalants were added, we see white bleached patches. Using the OCT, we saw mucus secretion as well as the skeleton. However, once we added the polyphosphonates, we saw huge areas of bleached coral. Tissue was gone. Polyps stopped moving. Basically, the coral was dying. We state that more research is key towards defining the safe dose, which is site-specific for these different chemicals, as well as the impact of multi-stressors in a climate-changed era. However, I would like to shift gears and highlight that the nexus is bidirectional. It's not just that desalination impacts the environment impacts the desalination industry. Low-quality coastal water will cause reduction in pretreatment efficiency and impair the desalination process by causing biofouling. We identified 3 key issues that are threatening the desalination industry these days. One is sewage outburst due to old infrastructure and poor maintenance. The second is induced jellyfish swarms due to climate change. And finally, which is my biggest concern to date, and I would wish that you will convey that message onward, are oil spills due to induced traffic of tankers. All of them probably will impact freshwater production. If you look into the outburst of this sewage, what you'll see is expedited growth of bacteria and algae because you eutrify the water. They will secrete polysaccharides, both passing through the pretreatment stages. Obviously, as was discussed yesterday, the desalination process is obligated to produce fresh water at a constant rate. Otherwise, they will be penalized. However, once you have fouling due to this sewage outburst, you have increase in transmembranal pressure. Once it's overdue 10%, it's no longer viable for the desalination industry, and they stop production. We saw it happening after 6 to 8 days. Similarly happens when jellyfish are being sucked into the desalination facility because they are shredded by the revolving drum. These again result in bacterial growth that are passing through the pretreatment with jellyfish parts, ending up, as I call it, jellyfish fouling. When you look into it, those jellyfish, you'll find parts of the jellyfish on the membrane as well as expedited biofouling. We find decreased pretreatment efficiency and dramatic increase in TMP 6 days since the jellyfish were drawn. but something else happens as well. Here, unfortunately, I need to go into molecular science a bit. What we find is those epsilon proteobacteria. Again, you should ask yourself, who cares? Who cares about this molecular stuff? But these epsilon bacteria, Acrobacter, when they are forming biofouling on the membrane, they secrete toxins, low molecular, with the charge is very small, toxins. Now the question whether when you have a very severe swarm, will that pass into my drinking water? This is something we currently do not know. My final example will be on these oil spills. This is a small one happening about 20 kilometers offshore of Israel. However, it ended up across all of our shores. People ask me after it happened again, who cares? Who cares because oil is highly buoyant. The intake ports are about 5 to 7 meters deep, so why should something end up in our process? Together with Professor Eyal Rahav, we constructed a large-scale desalination pilot in Haifa, where we have a 3 cubic meter feed tank that we mimic oil spills, followed by a pre-treatment similar to Hadera desalination facility and an RO system. The first question was, how much will be drawn? And if it did, what derivatives are passing through the process? Well, this is an ongoing project. We're in the midst of it. This is after about 6 months of work. So please don't tell anyone about that, although it is online. After about 4 days, we saw a drop in permeate water flux. Now, it should not happen because we want constant flux. But what happened is that TMP rose to the max operational procedure to 75 bar, basically. After 3 days, we had to halt the experiment. And this is 5 experiments that we tested one after the other. Autopsy of the membranes showed that even after coagulation, sedimentation, micronic filtration, we still had oil derivatives on the membrane. The big question now, will low molecular weight oil derivatives pass through the membrane and into our drinking water? Nonetheless, and regardless to what I told you, you go to managers of desalination facilities in Israel and ask them, what will happen if oil gets into the desalination process? The answer is simple. We have a downtime of 6 months to 1 year. No freshwater production if that occurs. These days, at the Zuckerberg Institute, together with Dr. Avner Ronen, we are trying to develop smart pre-treatment barriers. If you ask me in the discussion, we can continue to talk about that. But we also try to steal other people's ideas with fancy membranes that we can then clean in a more harsh conditions. I know my slides are black now. I want to move and give some more, I would say, positive note and a bird's eye view of how I see those things running up now, and conclude that Israel is pushing the boundaries of desalination, producing a lot of water by large-scale desalination facilities. But I'm more proud, not at the desalination facilities, but the fact that we are leaders in desalination innovations. And it's not stopping at freshwater production. We are pushing the boundaries of advanced wastewater treatment, as people talked about today. And currently are #1 in the world in wastewater reuse by HIPS. I would like to end by a question that a lot of people ask me in presentations. How come Israel, 9 million people, small nation, has become this water trailblazer. The credit needs to go back into our first prime minister, to David Ben-Gurion and colleagues, when they coined that water is a strategical asset in Israel. This is making Israel, the state, look forward and plan widely. With that, I would like to thank you. And as you see my shirt, I think this is important to remember, because we are in I would say, troubling water these days. And even so, I do want to get you back to Israel, to our International Water Summit. At this point, it's on May 5th, 6th, 2025. And with that, I would like to thank you, and we can talk about questions in the end.
Great. Hi, everyone. So, second day, you're maybe a little bit tired. I had lunch. You have this low blood sugar time. And here I am talking about economic, social, and environmental challenges. And when Sharon asked me to come, and talk here, I wasn't sure how I fit in, because my entire career I've been more of a technologist, studying things like water reuse and chemical contaminants and their fate. But I also remembered that I was the master cartographer at NAUI, and I had been chosen for that job in part because I had experiences through my time in California working with water reuse and on the National Academy's Science, Engineering, and Medicine Water Reuse panel, thinking about these things. And I'd learned a lot about the fact that it's not purely a technological challenge. And so I realized at this meeting, we would spend a lot of time talking about great technologies and great research, but there really was an underlying purpose for this meeting, and it was asking the question, where is all this going? So Israel's built seawater desalination and reuse. Parts of the United States have built in their own desalination, but maybe reuse to a larger extent. And when those systems wear out, we'll replace them. Maybe we'll replace them with more efficient systems. But the real question is, what happens in the rest of the world as climate change leads to greater water scarcity? And I think Israel and the United States have a lot to say about that. And I don't think I could give the story of Israel. I think we've heard a lot of it just this morning. But I think I can give you a little bit of a perspective of what has happened in California over the last few decades, where it's going in the near future, and what this could mean internationally to the future of water reuse and desalination. And I hope that can point to areas of research, both collaborative research and research for individuals. So that's my goal here. So I want to think beyond technology, and this morning we heard about ISLE Research as an organization that brings people together. Sitting in on one of those workshops with ISLE, I learned about this acronym PESTLE. And as a chemist who used to work with mortars and pestle, it stuck with me. So I have a pestle, and I can think about political, economic, social, technological, legal, and environmental challenges. These are the factors that determine whether a technology will diffuse and move on from the laboratory into actual use. Now, we've heard a lot at this meeting about technology, and we all love technology, and that's what we mostly do. Saying things about politics can be a little bit dicey. We all sat around last night and watched a presidential debate. I'll just say that essentially everything is political and can be politicized, and a lot of what will affect the movement of desalination is political. I also don't want to say much about legal standards and the law, because I know lawyers are inherently litigious, and I don't want to get sued by lawyers for straying into their territory. So I want to talk about economic, sociocultural, and environmental aspects of desalination and reuse to see if we can understand them better. And I've had three great teachers in this who come from outside the technological area. My colleague David Zilberman at Berkeley, who's an ag and resource economist, has taught me a lot about how economists think about this problem. My colleague Christian Binz from EWOG in Switzerland thinks about technology diffusion and innovation, and he's taught me a lot about these issues. And then Mike Koparski at the law school keeps me out of trouble with the lawyers. I've also had other collaborators, Manel Garrido-Bezerba, who I'll tell you about his research today, Jen Stokes-Drought at Lawrence Berkeley Lab, Cornel Rabai at University of Ghent, and Megan Mauder and Peter Fisk at NAUI. And so they're all working with me, but they don't get pictures in part because these three are more beautiful than the other ones, and also because they're technologists, and I want to emphasize the connection to the social scientists. So let's take a look at seawater desalination first. This is a map showing you the locations of seawater desalination around the world. And if you look at it carefully, you'll see there's a hotbed of seawater desalination around the Mediterranean. Probably Israel has too many of these dots to see, but most of the dry countries in the Middle East have seawater desalination plants. There are these desalination plants at all the capital cities in Australia, and there's a few in the United States, both brackish water and seawater. But actually, there's not a lot of desalination in the world. Look at China and India, over 1 billion people, and they're very much underrepresented in terms of desalination. So the next forefront with respect to desalination and reuse, or desalination, is clearly going to be whether China adopts it, whether India adopts it, whether all of these water-stressed places that don't yet have desalination end up building desalination. Now, I could try to put water reuse on this map too, but it would be messy, and it would be small, the symbols, because the hotbeds of water reuse tend to be, I guess, Israel, which we've heard about, California and Florida and Singapore and a few other places. But the amount of water that's being reused is actually smaller than the amount of water for seawater desalination. But remember, most of the wastewater in the world is not being treated today. And we're about to build lots and lots of wastewater treatment plants to address global sanitation problems. And we're going to see megacities develop, and they're going to need some form of urban drainage and sewage disposal. So I want to tell you about a little story about California so you can see how this is played out in the United States. And I think California is the best example of water reuse in the United States because we've been at it the longest. So this figure shows you, and I apologize, million acre feet per year. It's about 800,000 cubic meters to, 800 million, I guess, cubic meters per year is an acre foot per, a million acre foot per year. But what you can see at the top is the amount of wastewater produced in California in 2020, and you can see the amount of water that was reused in California. And I want you to pay attention to these three phases. An initial phase of water reuse in California before 1970 to about 1990, where most of the water reuse was for agriculture. So we did what Israel did. We took water from our cities that were near the farms, and we treated it, we chlorinated the heck out of it, we filtered it, and we used it in places like Monterey. We used it like outside of Fresno and Modesto and Bakersfield. And that was water reuse. We had some purple pipe projects that used landscape irrigation near cities, but that's how we did it. But starting in the 1990s to about 1990 to 2015, you can see growth in water reuse in places like the Santa Ana region, which is where Megan was telling us earlier about Orange County Water District, Inland Empire, a few other places, doing mainly indirect potable reuse, putting water through advanced treatment processes, injecting it into the ground, becoming part of the water supply. And in about 2015, a severe drought led the politicians in Los Angeles and San Diego to commit to essentially following Orange County's lead. And now we're at a point where we're projecting that something like 70% of California's wastewater will be recycled. As you heard earlier today, Orange County doesn't have any more wastewater. They're looking to their neighbors to give them more wastewater that they can recycle. Los Angeles and San Diego hope to be at the same place. So water reuse is essentially done in California, at least at the centralized type of water reuse. Let's talk about desalination in California. This map from the Department of Water Resources shows you the location of desalination plants in California. I did not try to plot it on the same plot that I had for water reuse because it would be really tiny. It would be lost at the axis. So today, we only desalinate about 15% as much water as we reuse in California. And our water reuse is primarily brackish groundwater reuse. I'm sorry, our desalination is essentially brackish groundwater desalination. We have one major seawater desalination plant at Carlsbad, which is responsible for something over 90% of the desalinated seawater. We have the small plant at Santa Barbara, which Megan talked about on the first day, which is about another 5%. But the majority are these brown circles here of inland brackish groundwater desalination. And I think it's important to look at how we got to this place. So the reason that we chose to go with potable water reuse instead of seawater desalination in California, and I'll assert to you the reason we're likely to continue investing in potable water reuse and unlikely to build more seawater desalination plants in the coming years, is something referred to as legitimization. So I had a student, Sasha Harris-Lovett. She worked with Christian Binns, and we kind of co-advised her with Christian's supervisor, Bernhard Trufer, and we looked at this concept of legitimization. So when we started looking at this in the early 2000s, we had this period before us where potable water reuse projects had been rejected by the public, in part because of this idea of the yuck factor or toilet to tap. But through the efforts of Orange County and other water districts in Southern California, we saw potable water reuse reach a point of legitimacy. And the legitimacy came from three types of legitimization that is seen over and over again as technologies undergo this transition from new and unfamiliar to being accepted by the public. The first was pragmatic legitimization. You can read about this in our paper on it, but the idea is that the utility talks about the project as serving the public's interest and creating a safe water supply, not as a way of disposing of sewage, not as a way of finding a cheap way to provide water, but as a way of being green and sustainable and resilient in the face of climate change. The second type of legitimacy that has to occur is moral legitimacy, and that is that the public has to trust the people doing the water reuse. And this involves things like trust in the utility because they're open and transparent about what's going on. They don't try to brush problems underneath the rug, and they trust the regulators to look out for the public's best interest. And Orange County Water District and other utilities and the state regulators did a lot of work to create a system of regulating water reuse that created legitimacy. And finally, they have type 3 legitimacy, cognitive legitimacy, where people have experience with water reuse. And when they have experience with water reuse, they're familiar with it. They drink the water. So when you go to Orange County and go on the tour of the treatment plant, you get a little bottle at the end and you try it, and it tastes just like any other water. And those three things together created this legitimacy. And now when a new potable water reuse project is proposed in Southern California, you don't hear anything from the public. You don't have people wanting to reject it. You don't see articles in the newspaper about toilet to tap, and that idea is spreading around the rest of the United States. So when projects are proposed in Colorado and Texas and Arizona and Georgia, they're generally accepted by the public, and you don't see this rejection. So when I hear people say, well, our country or our people would never accept potable water reuse, I think you forget that there's this process of legitimization that has to take place. That stands in stark contrast to what happened with seawater desalination in California. Christian and his colleagues at AVOG wrote this wonderful paper that came out in 2022 where they traced the discourse about seawater desalination. I don't have the time to get into the issue in a lot of detail right now, but what happened is different groups talked about seawater desalination in different ways. Some people were proponents, like the company that was trying to promote it, Poseidon. Some people were opponents, like the people who were investing in potable water reuse, and other people just question the impacts, like we just heard about in the previous talks, of desalination on the ocean environment. And so it became quite contentious, and the private company, which was responsible for the proposed seawater desalination plant, became a little bit of a villain in the eyes of the public. And so when that happened, people became very suspicious of the profit motive behind a private company trying to build a public-private partnership for water. And it went against the face of the way in which legitimization tends to happen with water in California. And as a result, when we get proposals for large seawater desalination projects in California, there's organized public opposition. So this project, the Huntington Beach project, which was rejected by the Coastal Commission in 2022, or the approved project in Monterey, which barely squeaked through by a small margin and may or may not end up getting built ultimately, or even the existing Carlsbad project, which still faces public opposition from the environmental community. It really is a different environment when we think about the future of desalination in Southern California. So that's kind of like a little bit of a story about successful legitimization of potable water reuse, kind of unsuccessful legitimization of seawater desalination. Let me tell you where this is going next. So when we think about water reuse, I showed you the story and I showed you this map, and it gave you the idea that potable water reuse had reached the end of the line because we have plans for reusing all the water, but that's not the end of the line. As we heard in our keynote on the first day from Megan, there's this idea now that before we send the water to the sewage treatment plant, we can recycle it at the building scale. And the city of San Francisco has a wonderful program where there's an ordinance requiring large buildings being built in the central business district to have membrane bioreactors and different types of treatment plants in the basement to treat that water through advanced treatment and to reuse it within the building for toilet flushing, for cooling towers, for other types of applications. And we've thought about these projects and we're very impressed by some of the technologies, and they really fit into the kind of way that now we approaches the world. But we also realize that there's a chance that it could become a dead end because these systems require dual reticulation plumbing, and there are not a lot of buildings in the world with dual reticulation plumbing. So it would be for new construction only, and we're not building houses and buildings very quickly in California. So I've been thinking much more about this idea of whether we could have building scale water recycling and use the water for potable purposes or near potable water purposes. So in 2022, I was part of a team that did a techno-economic analysis on this idea of building scale water systems where you could essentially be net zero water. And produce all the water you need over the course of the year, maybe with a rainwater tank on the roof, or maybe with a small supplement of water from outside. And what we saw in this analysis is that the water was relatively expensive, between $1.5 and $2.7 per cubic meter. But if you recognize that this is the price the consumer pays and not the water utility, it actually has a return on investment in fewer than 10 years. And so it really becomes attractive to the people who might use it. And so we could see at current tariff rates in North America and Western Europe, this being quite attractive to utilities. And because the water utility doesn't have to pay for the new infrastructure, it could be a way to meet increasing demand or make up for shortfalls due to climate change. The other thing that's quite interesting about this idea of building scale water reuse is that the public not only accepts it, but may actually become quite enthusiastic about it. So we have a paper, it just came out, I think, yesterday online in Nature Water, where we looked at something that looked a little like Barcelona's superblocks. And if you know anything about the superblocks in Barcelona, these are these housing areas where people live in accord, and they're meant to be like greener living and more communitarian living. And what we did was we did an analysis to see if you could integrate vertical farming and nutrient recovery from the wastewater and grow your own food and sell the food to help offset the price of the water treatment system. And this too has a return on investment of fewer than 10 years and probably engenders a lot of interest and enthusiasm. So these social, cultural support for new technologies that might let it diffuse. So that's kind of where I think reuse is going in some of the wealthy countries in the world. I also think desalination has a future. And in California, the future of desalination is probably some smaller seawater desalination plants. I talked with Sharon about this a little on the first day. I hope we talk about it more later. But I think the future in California is going to be more brackish water desalination. But we have a problem. And that problem is what to do with the brines. So what you can see on this map is I circled two areas, the Oxnard Plateau and the Santa Ana River or Inland Empire. And these are, if these were scaled properly, these dots were the proportional size to the project, you would see that these are some of the biggest groundwater desalination projects in California. And they're made only possible because they have brine lines that take the brine back to the ocean. And so if you're inland, it's really hard and really expensive because we don't know how to get rid of the brine. Now, this issue of how to get rid of the brine brings me to a project that we started in Naui when we started thinking about the circular water economy, and that was this question of whether desalination would ever have a role to play in agriculture in trying to address the issue of waterlogging and salinization. And so we've been thinking about this, and we were originally inspired by a group of farmers in the San Joaquin Valley who came together and formed an organization referred to as CV Salts. And this is I guess, a stakeholder-led organization, a consortium between the farmers and the state regulators. And when they thought about the long-term problem of farming in a closed basin where the salts were accumulating, their solution was to build a series of about 30 desalination plants, probably about the size of that project in Carlsbad, and a great big pipeline to take the brine all the way to the San Francisco Bay. It would have cost over about $8 billion, and the water would have been something like, I don't know, $4 a cubic meter or something like that. So this project is never going to get built, but the fact that people talk about it makes you realize that it's an existential threat to a large number of people. And so following up on some research that Megan published in 2017, we started thinking about this idea that there's more granularity to the value of water in California's Central Valley for agriculture, and it has to do with the profits that individual farmers can make by growing high-value crops and the availability of water. And you can already see that in some parts of the valley, farmers are willing to pay about $1,000 a cubic meter, or an acre foot, or about $1 a cubic meter for their water. And so it gets close to the price of what we could do with brackish water desalination. And so we've been thinking in our project about small-scale brackish groundwater desalination plants that can be set up close to the farms that have the greatest water need and the highest profitability to start to build an industry and build expertise in this. And over time it spreads because this process of learning by doing that social scientists talk about, and the creation of an industry and creation of regulatory structures, makes these things get cheaper over time. So the natural early adopters are the farmers who grow walnuts and almonds and live in places where there's not a lot of water. But what we found as we've dug into this issue a little deeper, as we've talked to water utility experts, as we've talked to people from the industry, there's a problem. And that is still, you need something to do with the brine. And you can't build a giant pipeline if you're going to build a series of small desalination plants, because it would have to be a tiny, tiny pipeline. And the alternative of putting the brine in trucks and driving the trucks to the ocean is also quite expensive and not very acceptable to society. So this idea that Pei Xu studies in her research of, and this is a figure from some of the research that you saw on the first day, of actually taking brines and valorizing them, of taking the brines and creating useful products to them, gets quite interesting. And in the context of agriculture, it really is the circular economy, because you need calcium and magnesium and potassium and sulfate to grow food. So you make the gypsum instead of bring it in. And that really starts to get interesting, and we're very excited about that. Now, I'm also trying to think beyond California and beyond the United States, and to think about where reuse and desalination will go in the future. And so I think that for water reuse, the real opportunities are not necessarily in the wealthiest countries in the world, but the rapidly growing cities in low and middle income countries. And the example I want to share with you is Bangalore in India, India's version of Silicon Valley, where they too have a regulation that requires new buildings to have in-building water recycling systems. But the systems that they have in Bangalore are a little more primitive than the ones you might see in San Francisco. but they're increasingly becoming sophisticated, and people are borrowing these technologies that are being developed in places like San Francisco and New York and using them to create potable water recycling systems at the building scale. And when you go to Bangalore now, it's starting to become a sales proposition for the builders of new buildings for the wealthy that their building can provide potable water because the city can't provide potable water all year round. And so when you think about how you live in India, how you might drink bottled water, you might boil the water that you bring into the house for cooking, but you'll shower and bathe and wash your clothes in water that might have pathogens in it, for example. You could see how this could grow and become more of a thing in low and middle income countries that are rapidly growing. And I think when you think about the explosive growth that we expect in sub-Saharan Africa and other parts of Asia and South America in the future, this could offer an alternative to the centralized water supply paradigm that we've all been saddled with for our whole careers. Now, thinking about desalination, I know that we'll have large desalination plants built around the world. In fact, one of the things that happens and one of the reasons why you see these mega projects being built is that the stock of multinational companies becomes more valuable when they put a tender out for a mega project. And so in some ways, financial speculation allows these giant, 200 million gallon a day seawater desalination plants to be built in the Middle East. But I don't think that's sustainable, and I don't think that's the future. I think as researchers, we should be thinking about other avenues for our desalination expertise. One is the issue of water kiosks, for example. In places where people have not realized the human right to safe, affordable water, individual entrepreneurs are putting in, and NGOs are putting in water kiosks and using desalination technology to turn contaminated groundwater and contaminated surface water into safe drinking water, and they're competing with the Nestle's of the world and the trucked water and making their own water. And it's an interesting problem of how to run a freshwater desalination system without an antiscalant, or without highly trained operators present. We should be looking at those kinds of problems and not just focusing solely on this giant mega treatment plant industry that already is doing quite well on its own. And then finally, I wanted to put a pitch in here for thinking about desalination in agriculture. Last spring, I got to participate in an event at the FAO in Rome, and the FAO is starting to think about this question of desalination in agriculture, and we're already starting to see Spain and Malta and many of the countries, Morocco, many of the countries in the Mediterranean investing in seawater desalination plants for agriculture, and the kind of knowledge that's been acquired in Israel, the kinds of thinking that we're doing in California. I think it's a really good time for us to think about what we've learned and what the problems might be in the future. So let me kind of end here with giving you some final thoughts and maybe seeding some questions for our discussion. I think I told you that centralized desalination, the big desalination plants, and centralized water reuse are going to become more accessible to more people facing water security challenges. These become more reliable and cheaper over time as more of them get installed. So that's always going to be there for us. Thinking about the political, economic, social, legal, the pestle, right, of issues is important because these play a large role in the diffusion of the technology, and it's on each of us to become educated about more than just our technology if we hope to find the right kind of research to have an impact on the world. So us researchers need to consider the context for our technological innovations and not only think about how they're going to fit, but think of a theory of change, how what we do is going to lead to acceptance by society, investments by society, and acceptance by society. And finally, I think there are a lot of opportunities in this area of premise-scale potable water reuse. I think this question of brine valorization and brine management is really important, and I think the use of desalination in agriculture are really great issues, and we need to study them more. So with that, thank you for your attention. I look forward to the discussion later.
All right, the end is near. Okay, so this has just been an outstanding event. I've heard so many things that I wanted to tie to my presentation, but I told myself, okay, don't do that because it's going to get too distracted, but I have to just say one thing up front. I loved Ito's video of the concentrate leaving the seawater RO plant, that it's a river. Not too long ago, my students and I were set on finding the waste that's discharged from a wastewater treatment facility to show, hey, look, this is all the water that's being wasted. And we would show that and how we're going to reuse that. And we thought that would be a very impactful clip. And we finally found one. Come over, everybody look. And we're all watching, and you have the blue seawater and the brown water coming out. And we were all like, I don't think that's going to be the best. Hey, let's drink this water. So, okay, that was, I'll try to avoid too many asides. I realized I did not update my short bio because I'm no longer Director of Environmental Engineering. I'm instead Director of the Rewater Center, which is part of the Water Reuse Consortium. And as part of that, we publish, along with Trussell, who writes the Potable Water Reuse Report. And we have issue 3 coming out maybe even this week, and it's an international perspective. We've done a California perspective, a U.S. perspective, and this one's international. So if you're interested, let me know. I'll make sure you'll get it. All right, so let's get started on integrating systems of desalination and potable reuse for flexible water supply. I wanted to just start by telling you Bana Dada is my PhD student who just has done this work that I'm showing. We recently pulled on 2 colleagues, Andy Salveson and Tom Secord from Carollo Engineers. And this is a body of work that started in 2020, actually, and Zahi will like it if I say this. It started with osmotic dilution and salinity gradient energy using PRO. I think soon, even before this came out, those processes kind of fell off the cliff. But sometimes we ask, did anything good come from that? Well, yes. I think the body of work that I've had came from that moment of bringing 2 streams together and making use of that salinity gradient energy that now actually we fight the increase in entropy in our current work. But so something good came of that, and I'll talk very briefly about projects 2 and 3 as I go. So let's get started. I thought I'd start with a place that was very comfortable and familiar to all of us, the groundwater replenishment system. You know that it's the world's largest indirect potable reuse system. It's been operating since 2008. It's a joint partnership. I would underline that because sometimes that's a hard thing to achieve, between OCWD and OC-SAN, where they take highly treated wastewater that would have gone to the Pacific but now is being used for reuse. Here's the part that maybe you don't know, which is that the expansion. So OC-SAN was facing the challenge of having to build a second ocean outfall 5 miles off the coast of Huntington Beach. Needing to address 100 MGD of flow relief, it approached OCWD to see if it would be willing to build an expanded project. Then I show you Point Loma, which is here, which is a wastewater treatment plant in San Diego, California. It's been operating since 1963 under constant waivers and renewal of waivers to the Clean Water Act. It's the only facility in the U.S. that discharges primary effluent to the ocean. Environmentalists and surfers did not like that. They were pushing for upgrades, but you could see that upgrades here might not be so easy. And footprint is something that I think about a lot in my work, and some of that came from working with Singapore. But anyway, eventually these environmentalists saw a better option, and ta-da, along came Pure Water San Diego, which is the largest infrastructure project in San Diego's history. Potable reuse, from that, I'm not distinguishing IPR or DPR here, will provide nearly half of San Diego's water supply locally by the end of 2035. So half of a water supply from potable reuse. And this came after years of legal wrangling over sewage. And they said, what if instead of trying to clean up the water that was going into the Pacific, we try to reduce the amount of water being dumped there? So here's the takeaway from those stories. These early large potable reuse projects and expansions have had the primary purpose of reducing discharge or meeting water discharge regulations. Their added benefit is providing high-quality effluent for water reuse. Kind of a different way of looking at it, and David alluded to this earlier. So, in our work, we've been looking at the scenario of wastewater effluent coming into a wastewater reclamation facility, going on to an advanced water purification facility, and then being used for potable reuse. Of course, downstream from this, you could also have your drinking water treatment facility. We get really excited about these facility diagrams. And in California, full advanced treatment, which includes RO and AOP, it actually does not include microfiltration, but we're going to be including it. But it requires reverse osmosis and AOP. And that's good. We think of that in terms of public health and CECs, but also it's really important because our wastewater has increasing salinity levels. And that's due to consumer devices, industrial inputs, upstream desalination, but also conservation. And in low-lying coastal areas like Orange County Water District, it also includes seawater inflow and infiltration. So in low-lying areas where you have corroded and aging infrastructure, ocean water can come into the system and basically intrude into your wastewater reclamation plant. This is not limited to Southern California. There's been a lot of studies on it in the Seattle region and other places. But the beauty of using the reverse osmosis is that we can use that existing RO to treat the additional salinity. In Orange County's case, they had to throw in a booster pump, but still you can use your existing infrastructure. So in our second study, what we looked at was first, we acknowledged this ability to treat these higher salinities with your existing infrastructure. And then we said, can we take this further? So our question was, can we use the existing RO system to treat even higher salinity? So bring in waste streams that would not normally be treated here and use that to provide additional supply. And this was of interest at Orange County Water District when they were expanding from 100 to 130 MGD. And they had a moment where they were looking for that additional 30 MGD. So we suggested you could bring in a regional brine interceptor, which consists mostly of brackish water RO brines, and but we were generalizing. You could bring the brackish water RO brines or the interceptor upstream of the wastewater reclamation facility, depending on how much pretreatment it had, depending on what's in it, or downstream of the wastewater reclamation facility. And we looked at scenarios with and without seawater I&I. And we then kind of after we thought about what we did, we now refer to this seawater I&I as incidental, unplanned, or de facto seawater desalination. See how we did that? We took the potable reuse de facto and brought it to desalination. But we said, can we transition from this de facto seawater desalination to doing intentional desalination at this facility? Because there's so many similarities between the advanced water purification facilities and the seawater RO facilities. So essentially that would be, or Not essentially, but simplified, that would be just bringing the seawater in. And we knew this was somewhat possible because study 3 from earlier on, that we worked with Dudek engineers and with the Doheny desalination plant. So I'll show the figure first. We came up with a schematic for augmenting their ocean water desalination facility, their future ocean water desalination facility, with potable reuse. And we looked at that in terms of cost and environmental impacts. So if CapEx and OpEx is your thing, this paper has tables of dollar signs. So basically what I'm showing here, well, first, this is the 5 MGD seawater RO facility that they are currently designing. And this scenario was they're already thinking about upgrading that to a 10 MGD facility. And where we came in was we said, well, why not do potable reuse? Because at the same time that they're building a seawater RO facility, they were also sending their wastewater out to the sea, out to the ocean. And so we show scenarios that we called, let's see, I'm going to do it this way: ocean raw water augmentation, ocean treated water augmentation, so we used the DPR terminology, and then a full integrated facility. And really, when we came at this, we were thinking in the integrated facility, but we kind of backed off and looked at the advantages and disadvantages of different ways of combining these two facilities. So the takeaways were, and again, these takeaways are compared with expanding the 5 MGD seawater RO facility to 10 MGD. I knew I was going to do that at some point. There we go. Are making maximum use of the wastewater resource to augment our potable water supply. No more sending that wastewater out to the ocean. Reduced environmental and construction impacts, and a competitive cost of water production. So a key thing we found is if we could have the benefits of augmenting at essentially the same cost. So that's kind of all background for our current study, conceptualization of seawater augmented potable reuse, where we're asking how and where can we integrate the seawater into existing AWPF infrastructure and process streams. This is where we had been wanting to go because, as we've discussed, as David's talked about, in California we have a lot of potable reuse and existing facilities. So we're thinking, wouldn't it be great if you could use those facilities to treat seawater as needed, supplement with seawater, and then you don't risk having a stranded asset of a seawater RO facility. We did the pit stop with Doheny because Doheny had over a decade gotten all the permits gotten everything in line to have a seawater RO plant. Over that same decade, as potable reuse is developing, that's great, but once they have those permits, they didn't want to switch gears. And but we thought the scenario of augmenting a seawater desal facility with potable reuse was also interesting from a rest of the world perspective, from Israel, from a Australia perspective, where you have existing seawater desalination facilities and might want to bring in potable reuse. Okay, back to the current study. So basically, it's looking at the parts: the wastewater reclamation, the advanced water purification, the seawater desalination pretreatment, where we bring the seawater in. So for the treatment processes for advanced water purification, we relied on the California Code of Regs for IPR and DPR and collaboration with Andy Salveson. For seawater desalination, we really relied, this was a great guide, on a plant performance and selection guide that came out by the Water Research Foundation and collaboration with Tom Secord at Carollo. And we selected the seawater augmentation locations where we're bringing the seawater in with two objectives. One was to use the existing AWPF processes to the fullest extent possible without sacrificing the treatment of wastewater, the potable water production, and to implement as few additional processes as possible. This is a first cut. We might go back and say, why are we trying to implement as few additional processes as possible? We were just kind of basically trying to make it more palatable. So, ta-da, 4 treatment trains conceptualized. This is like the end coming first. So these are them. And the only thing I want to point out on this page is that there's 2 IPR scenarios, indirect potable reuse scenarios, 2 DPR scenarios. These top 2 use conventional activated sludge for the secondary, and these bottom 2 use a membrane bioreactor for the secondary. And then what I'll do in the next slides is walk through these. So this was our IPR treatment train. So we have our wastewater reclamation with activated sludge, our advanced water purification. You'll see that we, before every MF or UF step, we've got microscreens, and before every RO, we have cartridge filtration. So just keep that in mind. And we looked at different seawater qualities. So as Ido pointed out earlier, oil makes a difference, and we know algal blooms make a difference. So first we considered an open ocean intake, seawater with normal conditions, and, and we simply brought that into the microscreens right upstream of microfiltration. We added in additional screens, but we kept this kind of the simplest scenario. Then we went to, for seawater subject to algal blooms and or oil spills, and we added a dissolved air flotation with coagulation beforehand. I had a lot of hesitation doing that because I know there's a lot of anecdotal stories that are not in support of dissolved air flotation, but right now it still seems to be the industry standard, especially for algal blooms or oil spill situations. And then that comes into the microfiltration. We also considered if you have a subsurface intake, where would you bring that in? Of course, you're making use of the subsurface filtration. And so we show that coming in right upstream of the reverse osmosis. If you do have ferric and manganese in that subsurface, which was a problem we learned about in the Doheny study, an expensive problem, which makes us think, our subsurface intake's always that great if you have to add on a pretty significant pretreatment step here. In the IPR treatment train with an MBR, so here, of course, we're taking the microfiltration that would have been here and putting it into the membrane bioreactor. And what that does is basically shift all of our schemes to the left. And so we've got our open ocean intake, our seawater under normal conditions, and this was a lot of debate of how do we show this? And again, this is first iteration. You guys are seeing this hot off the press. So we show an opportunity to bring it into the membrane bioreactor, mostly for more biofouling control, but also just to keep, again, the process the simplest. But I know biological people in here are like, don't do it. So I'll talk about it a little bit more in a minute. But we also show the opportunity to bring it into conventional membrane filtration, and then it would go through the advanced water purification processes as well. So for the high algal bloom or oil spill situation, we bring it to membrane filtration, but we also show an opportunity here to bring that up through the membrane bioreactor as well. And we would consider that to be the more conventional step, but also more processes need to be added to make that happen. And the DPR treatment train with conventional activated sludge. So I think I can walk through this one pretty quickly now, except a key thing is with the DPR treatment train, we add in ozone BAC at the beginning. This breaks down the complex organics and helps with fouling and biofouling. So it generally improves the efficacy of MF and RO membranes and also the UV AOP process. So right now, the state of California requires this ahead of microfiltration. That's why we have it here. But we also realize if we're augmenting with seawater that contains bromide, if we bring that into the ozone, not only would we increase the ozone dose required, we'd form brominated DBPs. So for that reason, we stay downstream. We don't mess with the ozone BAC and stay downstream. In the future, maybe there could be some benefits into tapping into the nitrification that occurs in BAC. For that reason, that's why we bring it into the microscreens. And then the last treatment train is DPR treatment train with MBR. And this is essentially the same as the last one you saw because we're still trying to stay downstream of the ozone BAC. So key considerations for implementation of seawater augmented potable reuse. One thing we didn't think about coming straight into it is that the introduction of seawater would require piping retrofits. Piping, we don't talk about that. We're process people. But basically, stainless steel piping and your selection of it depends on feedwater chloride levels, chlorine levels, and pH. So what we found is that we would need to retrofit the piping and the processes downstream of our augmentation location, and particularly depending on how much seawater we were augmenting. And so that's a consideration now you're moving from 316 to super duplex, perhaps. The RO process at the AWPF, which is our current area of work, it must have sufficient flexibility so we could look at different salinities and varying flows, because that was a key new part of this study is we wanted to look at different flow rates coming through the plant, not just different water qualities. So you could do this with a conventional multi-stage RO system with an additional booster pump. We used CCRO. It's easier to model. And last, the biological processes. This is kind of where we're going next. We start as good academics with a literature review, and then we plan to move to BioWin and then to pilot testing. But from the literature review, we know that water salinity can affect nitrification and denitrification, that microbial acclimation is required, so we need to add things slowly and allow acclimation time. And we also found out that if we keep to less than 10 grams per liter, probably the microorganisms can acclimate in several weeks. So that's promising, because what you'll see is we're under 10 grams per liter. So next, I'm going to show you results for the RO treatment process feasibility. These are just through simulations using wave design, and these are just first cut. So don't hold me to them when we publish. And as I mentioned earlier, we used CCRO because of the flexibility. You can uncouple recovery, cross-flow velocity, and permeate flux and get the flexibility needed. Okay, so we set up to look at this using several scenarios. The first was just a baseline scenario, that's just 100% wastewater. Then a feedwater shortage scenario where we looked at augmenting with 10%, 20%, and then 30% seawater. And that was to mimic an AWPF that was experiencing a shortage of treated wastewater. And then an increased production. So that was for an AWPF that had additional supply available and had that demand. You need the supply and the demand there. So we looked at 1 MGD for all scenarios, 1.1 and 1.2 for the increased production scenarios. And here I just show you feed TDS and how it increased with augmentation and increases with augmentation. We analyzed the seawater augmentation in terms of the feed water quality, maximum recovery rate, fouling potential, permeate water quality, RO concentrate quality and quantity, and specific energy consumption. Again, these are just all output from WAVE software. So here we looked at the feed water quality and maximum recovery rates. And we see, as I mentioned before, TDS increases as you would expect with seawater augmentation. And we were looking at where that came from. So we see the constituents that were introduced into the feed water with seawater augmentation, those that were increased due to seawater augmentation, and those that you have more in the wastewater than in the seawater, so they were decreased with seawater augmentation. And then we use that to look at the maximum recovery, and we looked at it based on 2 criteria. The first is based on feed water solubility limits. We determined those with online software, and we see 3 values here. We also looked at the maximum recovery rate at feed water pressure limits, recognizing that the membrane elements we were using had a maximum of 41 bar. And so we can see that the feed water pressure limits determined our maximum recovery for higher augmentation, whereas at lower augmentation, our recovery was determined by feed water solubility limits. And we saw our feed water our recovery go down to 77%. And if you're in the potable reuse world and you see 77%, you get kind of sad until you think, wait, let's also put this in the context of seawater RO, where recovery is 50%. So in that context, 77%, maybe not so bad. Then we looked at scaling. We looked at calcium carbonate, calcium sulfate, silica, calcium phosphate. You might not have expected calcium sulfate and calcium carbonate to decrease as we increase seawater augmentation, but then you have to remember that our recovery was decreasing. So, you know, we always talk about lower recovery, less scaling, but we really saw the benefit here because we thought, oh, we're adding these divalents, scaling's probably going to become an issue, but of course your recovery decreases, so scaling was not an issue, and that's just the recovery. So, antiscalant type and dosage were not affected up to 30% seawater augmentation. Sounds trivial, but if you're at a facility and maybe trying to make this conversion and you don't have to change your antiscalant or make more storage area for it, it's a benefit. So that was scaling. If we looked at organic fouling and biofouling, it was a pretty simple story, as you might expect. Just the feed TOC decreases with increasing seawater augmentation. That's a reduced likelihood of fouling and biofouling of membranes. Permeate water quality. I am only now seeing the red, so I will wrap it up. In terms of permeate water quality, we looked at what was regulated. We looked at EPA regulations and California state notification levels. In general, we found most constituents were well under regulatory limits, with an exception of boron, so something might need to be done in this case. Of course, that's the highest augmentation case. And we looked at RO concentrate. Things like lower nutrient levels can be beneficial in RO concentrate discharge, and but at the same time our TDS was increasing. But then again, we used this moment to compare to a seawater RO facility and said, okay, we're still within range of what you would get from a typical seawater RO facility for the concentrate. And flow rates increase with increasing seawater augmentation. Again, that's just because recovery is decreasing. And specific energy consumption, yay, that's the end. So we looked at the specific energy consumption. We reached from our baseline of 1.36, we went up to 4.2. So it does increase with increasing seawater augmentation. We have loosely compared these, but realize there's really not so much to compare. So I think the more important thing is for me to get to the takeaways, because I'll come back to the energy. But we designed an AWPF that's not only flexible to changes in water quality, but also to variations or fluctuations in potable water supply. Treating seawater alongside treated wastewater takes advantage of the almost duplicate processes required to produce both water supplies, may offer footprint savings in impacted coastal areas, but there is a trade-off for potable reuse demands to be consistently met without significant increases in coastal infrastructure and with minimum impacts to marine life and ocean water quality, slight modifications to the AWPF systems, and energy penalties. Nothing's free, flexibility is not free, and you pay for it with energy. That's it. And I would want to acknowledge the funding agencies. This is a cooperative agreement through the Water Reuse Consortium that funds our Rewater Center and also through our School of Engineering. Thank you.